This is Unit 5, Investigation 1, Lessons 5 and 6. Starting off with the entry ticket for Lesson 5, we're going to be considering the function 2x minus 8 over x squared minus 16. First, we're going to be asked to solve for the vertical and horizontal asymptotes. To solve for the vertical asymptote, we need to set the denominator equal to 0 because we do not want an undefined rational function. So if I do that, I have to add 16 to both sides, and I get x squared is equal to 16. I have to take the square root of both sides to isolate my x, and I'm going to be left with x is equal to plus or minus 4. For my horizontal asymptote, it depends on the powers of my numerator and denominator. I know that looking at my leading terms, I have 2x over x squared, which means my denominator is higher degree than my numerator, and that's going to automatically tell me that my horizontal asymptote is y is equal to 0 because of all of the patterns that we discovered from the last two lessons. We know that if the denominator is greater in power, the rational function, will have a horizontal asymptote at y is equal to 0 always. Now we need to factor both the numerator and denominator. So here we're looking for a greatest common factor on the numerator, and we're going to factor the denominator. So here I'm going to take 2 out, and if you distribute that 2 back in, you're still going to be left with that 2x minus 8. The denominator is going to be x minus 4 times x plus 4, and if you notice, there's no middle term here, so negative 4 plus 4 will give you that 0, but negative 4 times 4 will give you that negative 16. Lastly, they want us to evaluate for when x is equal to 4 and kind of figure out what happens to the numerator and denominator when we have that value. So if we do this and we evaluate, we can see that in both situations we have 8 minus 8, which gives me 0, and 16 minus 16, which gives me 0. So if x has a value of 4, both the numerator and denominator have the value of 0. The concept of development, we're going to be discussing this a little bit further. We saw here that we had 2 times x minus 4 over x minus 4 times x plus 4. Notice that we have x minus 4 on both the numerator and the denominator. That's going to be our biggest indicator that there's probably going to be some sort of hole. Okay, so it's really a great habit to get into, to start factoring as much as you can on both the numerator and the denominator so that you can be able to determine these patterns right away. So here, it wants us to graph this function. So if I go to my Desmos and I graph this function, I have it right here. And if I zoom in on the value of 4 on this function, which is the red line, I'm going to trace my finger until I get to the value of 4. And here you're going to see that on this graph, it's going to be labeled as an open circle. And it's going to be 4 undefined. Okay, so at the value 4, our function's undefined, meaning that our value cannot be 4. It's not included in our domain. So here, we're going to see that y is equal to undefined at that value, and that's what we're going to be formalizing as a whole, okay? So, looking at the example 1, we have 3x plus 6 over x squared plus 6x plus 8. They give it to us in factored form, and again, the first thing you should be on the lookout for is, okay, well, what's happening with my numerator and denominator, and is there anywhere that I might have a hole, okay? So here, I can see that I have x plus 2 as a factor on both the numerator and the denominator. So that's probably going to be a good indication that I'll have a hole there. But first, I'm going to start with my vertical asymptotes because all I need to do for that is just set the denominator equal to 0. And here, since they already gave me factored form, it's really easy for me to jump steps and say, okay, well, if I'm setting both of those equal to 0, I know I'm going to get the opposite sign. So I have x is equal to negative 2 and I have x is equal to negative 4. On my horizontal asymptote, I'm going to notice that, okay, well, if I look at the not factored form, I can see I have 3x over x squared. That's telling me my denominator has a greater power than my numerator, so that I know that my value for my horizontal asymptote in this type of situation will always be y is equal to 0, and there won't be any x-intercepts. So now we're gonna graph this function, so I'm going to go back to Desmos. I'm going to get rid of this one, and we're going to be focusing on this. So here I just wanted to show you that these two forms are equivalent because if you graph them, you're going to get the same exact line. Doesn't matter which one you graph first or second. These are the same. One is just in factored form and one is not. So here are our asymptotes that we solve for. And as you can see, there's kind of an issue here because at x is equal to negative 2, I have a line and it looks like I have some sort of intersection. That doesn't really look right now, does it? So I'm going to have to figure that out, but in just a second. So I know that here I have x plus 2 and x plus 2 on both the numerator and denominator. So it's going to make sense that I'm probably going to have a whole here. So I'm going to touch my green function, and I'm going to say, oh, at the value of negative 2, look, it is undefined. There is no output for this function, and it is not included whatsoever in the domain. So even though it crosses this asymptote, you can clearly see that because it's an open hole, it does not include that value. So it kind of skips. Think about like kind of skipping a stair when you're going up or down the staircase, right? It's just not going to be part of your path or your function, whatever shape you're walking in, I guess, right? So here, I'm going to go back to my PDF, and I'm actually going to fill out what my y-intercept is, and I'm going to fill out my domain. But before I fill out my domain, I already know that I have a hole when x is equal to negative 2, because I looked at that point and we saw that it was negative 2 undefined. So it's going to have to be accounted for in my domain. So here I'm going to have negative infinity to negative 4, union negative 4 to negative 2, union negative 2 to positive infinity. So notice that negative 2 is not included in the domain, and that's why I have parentheses. For 2 on the next page, we have f of x is equal to 4 times x minus 2 all over x squared plus x minus 6. First order of business is we have to factor that denominator, and I'm going to end up with x plus 3 times x minus 2. That's going to set me up really nicely because now I'm going to be able to solve for my vertical asymptotes. I know I'm going to set each factor equal to 0, and I'm going to get x is equal to negative 3 and x is equal to 2. For my horizontal asymptote, I can see that my leading terms will be 4x and x squared. So I can see that my denominator is going to be a greater degree than my numerator, which automatically tells me that my horizontal asymptote will be y is equal to 0, which also means that there is no x-intercepts. You're going to get your y-intercept from the graph, and you're going to make sure you're accounting for your entire domain, right? That does not include the two asymptotes. And now we're going to try to solve for our whole. So notice up here that we have x minus 2 as a factor in both the numerator and the denominator. So over here in the denominator is the red part that I factored. And on the numerator, they already gave you that x minus 2. So that gives me an idea that I'll probably have a whole at the value 2. But I'm going to go to my graph, and I'm going to double check that point. And if I go to that value 2 on my function, you're going to see that there's going to be an open circle, and it's going to be undefined. So think about it this way. It kind of makes sense because we know that our asymptotes aren't supposed to be touched or crossed. So this is basically telling us that every value on this function except for this value is going to be able to work. So that also makes sense because I know that it's undefined on my denominator. So either way, I just can't have that value. There's going to be a hole and it's undefined. If I look at the next example, here is a more complicated example, so bear with me for this one because this one's going to take a little bit longer. So we already have this function in factored form, but we want to make sure that we're counting for every single factor. And some people might overlook the fact that there is a power of 2 on this x minus 4 factor. So that's going to tell us that we're going to have x minus 4 times x minus 4. So it's going to be there twice. I can also see here that I have x plus 2 as a factor on both my numerator and my denominator. So that gives me a pretty good idea that I'm probably going to have a whole as well. So let's just start with our vertical asymptotes. I need to set my denominator equal to 0, which means in this case, setting each factor equal to 0. So I'm going to end up with x is equal to negative 2 and x is equal to negative 1 as my vertical asymptotes. For my horizontal asymptote, this one gets a little tricky. I have the answer already up here, but I just want to go through why that was my solution. We have x to the third over x to the second. So my numerator has a value that's 1 degree larger than my denominator. So that means I'm going to have a slant asymptote, which means divide the numerator into the denominator. So down here, I just want to do a little refresher of synthetic division. But before we get started, this is our function. And we have x plus 2 as a factor on both the numerator and denominator. So we can actually cancel those out because there's just no sense in multiplying by something only to just divide by it. So if we're going to do division, we're going to make our lives a little bit easier for ourselves. So we're going to cancel those out because they neutralize to 1 anyway. And we're going to have x minus 4 squared all over x plus 1. So here, if I distribute, I will get the expression x squared minus 8x plus 16 divided into x plus 1. So from here, I have to take my numerator and divide it into my denominator. So x plus 1 is my factor. And remember that we need x minus h format. So in order to get that, we have to have, and we have x plus 1, we have x minus a negative 1. So that tells us that our factor is negative 1. That's the only way to get x plus 1. So here, if I do my synthetic division, I'm going to drag down that 1, multiply by negative 1. 1 times negative 1 gives me that negative 1. Negative 1 plus negative 8 gives me negative 9. I got to multiply that negative 9 by that negative 1, and I'm going to get positive 9. And then as a remainder, I'm going to get 25. But the remainder doesn't matter. So if you think about it this way, we have x minus 9 as our solution, and then we have 25 over x plus 1. As x gets larger, we only have 25 in the numerator, and then we have x plus 1 in the denominator. So as x gets bigger, that 25 over x plus 1 is just going to get smaller and smaller and smaller and just less important, right? So it just doesn't really account for that much. It's just not significant enough to measure. So we're going to end up not taking the remainder. We're just going to take the quotient. So because we have 1 and a negative 9 here, we know that our horizontal asymptote should be y is equal to x minus 9. We're going to get our x and y intercepts from the graph. I'm going to go to the Desmos and I'm going to graph these. So here I'm graphing this function, and as you can see, it's kind of a different shape than we're used to. It's going to give me that indication that I should have a slant asymptote probably somewhere around here. But we know that our horizontal asymptotes are negative 1 and negative 2. And we actually also know that my slant asymptote is going to be x minus 9. So here is our graph, and you can see that here there's an intersection of some sort. So here we got to figure out what is going on. So we're looking for that whole value. So if you look here, we have x plus 2 on both the numerator and denominator, as we've already discussed. So if I go to my value where x is equal to negative 2, that's where I saw my weird intersection with my asymptote. So I'm going to touch this line, and I'm going to find that value where x is equal to negative 2. And we're going to see that it's undefined, okay? So that is going to be where our hole is, and we're going to indicate it with an open hole. So we have our x and y intercepts at 4, 0, and 0, 16. We can just confirm that using the graph. And then we have our domain, which accounts for every value that is not 2 or negative 2 or negative 1, because we have vertical asymptotes there and a hole, which we also need to account for with an open circle. Okay, so negative 2 is undefined, and that is where we're going to have our hole. Moving on to the application of rational functions, we're working with the function c of t is equal to 5t over t squared plus 1. This is describing the concentration of the drug in the bloodstream over time. So we have our c of t on the left, that's our y values, and that's measuring our concentration in micrograms per liter. And then on our x-axis, we have t in terms of time. So looking at this rough sketch of the graph, we will go to Desmos in a second to see the really accurate version. But here, our first question is asking, when will the highest concentration of the drug be reached, and what amount is in the patient's bloodstream at that time? So we know that by looking at even just like this rough sketch that we have a maximum at 1, 2.5. That's going to really be helpful because that's obviously when the concentration is the highest, right? So we just have to interpret this data point. So here we're going to say, okay, well, in 1 hour, the concentration was 2.5 micrograms per liter. And here, for the letter C, it asks, well, how long does it take the concentration to drop below 0.2 milligrams per liter? So that's actually when we're going to need our Desmos. And I put this into a table. So all the values 1 through 10, because that's the interval they were originally having us look at. But if you look at your value 10, when t is 10 hours later, we have 0.495 concentration. But it's asking, well, when does our concentration hit below 0.2 micrograms per liter? So I'm going to try different values here. I'm going to try 15. And okay, well, 15 is 0.33. That's not 0.2 or under. So I'm going to keep going. So let's go to maybe, let's say 20. Oh, nope, because we have 0.249. Let's try 22. Okay, well, 22 is still 0.22. Let's try 24. Okay, well, that's going to give us 0.20, and it could actually be rounded up to approximately 0.21 because of that 7 and 9. But let's try 25. Oh, that's 0.199. Well, our question asks us, well, how long does it take for the concentration to drop below 0.2? Well, 25 hours, because at 24 hours we still have 0.2 concentration, but at 25 hours that's how long it takes for it to drop below that 0.2 micrograms per liter. Now asks, well, what is my asymptotes? Well, let's start with our vertical asymptote. We need to set our denominator equal to 0. So if I do that, I'm going to subtract 1 from both sides, and I'm going to be left with t squared is equal to -1. Now, if I want to isolate t, I got to take the square root of both sides. But that's going to leave me with t is equal to I, because the square root of -1 is the imaginary letter I. So since that doesn't exist, and I can't make that into an asymptote on a coordinate plane, then we have no vertical asymptote. But if we look at our function, well, we have 5t over t squared plus 1. We have 5t over t squared, meaning our denominator degree is larger than our numerator degree. This is going to automatically tell us that we have y is equal to 0 as a horizontal asymptote, and there will not be an x-intercept. Lastly, it's asking, well, what is the meaning of the horizontal asymptote within the context of this problem? Well, I don't want you to overthink anything. I just want you to put yourself in this type of situation, right? So you're talking about concentration of a drug in your bloodstream. So we're talking about our asymptote being that x-axis, right? Because that's where our y is equal to 0. So if that's our asymptote, y is equal to 0 as that horizontal line on the x-axis. If you look at our graph, we skyrocket up for concentration within the first hour, but then after that first hour, it starts decreasing in concentration. And as we get closer and closer to positive infinity, it gets closer and closer to 0. If you look at your Desmos right here, and if we just plotted our y's equal to 0 asymptote, we could see here, and make sure it's a dashed line because it's an asymptote, we can see here that doesn't matter how far we zoom out here, that our function is going to keep getting closer and closer to 0. So, in the context of this problem, we're going to say, okay, well, over time, as time passes, the concentration goes towards 0. So, over time, the drug is leaving your system. So, we're going to be looking at a couple more realistic examples like this. We're going to do some live as a class, and we're also going to do some together in the problem set.